next speaker is Joanna Klein from the University of St. Thomas in Minnesota. Joanna, it's lovely to have you here, and we look forward to hearing about stories of antibiotic discovery.
Thank you, Chloe. That was a wonderful talk. I just affirm that, and also wonderful to see the mentors that you have in your life. I'm really happy for you, and I'm really excited to see what your career holds for you. So, yeah, great to have a young scholar here. So my name is Joanna Klein, and I am a microbiologist by training, geneticist also. And I'm currently teaching at the University of St. Thomas in St. Paul, Minnesota. And I've been there for just a year. Prior to that, I taught at a smaller private Christian college for 19 years. And that's how I was introduced into the ASA. I've been to, this is my fourth ASA conference. First time giving a talk. I've given a couple poster presentations before. And I thank ASA for hosting these conferences in wonderful places where I can take my family on vacation. And so, looking back at my memories on Facebook, there was Colorado. That was my first one, I think. And then there was Chicago. Actually, I think it was Boston first, and then Chicago, and now Toronto. And I'm overwhelmed by the metropolis that is Toronto. I had no idea. I was a little bit naive. When you see the blue dot on the map and you see where the school is, you think they're closer than they really are. And so I've spent a lot of time commuting into the conference, haven't been able to interact as much with the conference people as I had hoped to because my family is elsewhere and they're stuck in the hotel right now because I have the car. Anyhow, thank you for the opportunity to give a talk to you this morning. It's a Tiny Earth, Stories of Antibiotic Discovery and Student Transformation. And so an outline for my talk today is I'm going to touch on some scientific topics and hope that you'll learn a little bit about the antibiotic resistance crisis. I'll also talk a little bit about the soil crisis, although I'm not a scholar or researcher in that area. I'll talk some about transformative education. And so I'm an educator at heart. That's why I do what I do, is to kind of train the next generation of students. And so I have always used a course-based undergraduate research experience model in my laboratory courses. And so I'll tell you more about that. And then I'll foray into fostering a love for God and neighbor. My family, in addition to being stuck in the hotel right now, we are all Star Wars fans. And so Jedi Master, you know what a Jedi Master is, right? And so undergoing some Jedi Master training, and I've added an A there. This stands for anti-racism, justice, equity, diversity, and inclusion. And so how do those get incorporated into my teaching, into my practice, to foster a love for God and neighbor and the earth? So antibiotics, just a basic definition here, are natural or synthetic chemicals that kill or prevent the growth of bacteria. They are naturally produced by microbes. Penicillin was isolated from a fungus. An antibiotic called streptomycin was isolated from streptomyces. Many of these microbes are found naturally in the soil. And it's in the soil where the bacteria or fungi live in a competitive environment. And so it's advantageous for them to produce, chemicals, secondary metabolites that could promote their own growth in this competitive environment. And so it's to this source that you can look for new antibiotics. And the reason that we would want to look for new antibiotics is because there is a decreasing ability to treat infections, bacterial infections, with antibiotics. There's a growing incidence of antibiotic-resistant infections, especially in hospital-acquired illnesses. And that's partly due to the use and overuse of antibiotics in medicine, but also in agriculture and in other areas of life. And also the fact that bacteria just adapt, right? And so shortly after an antibiotic is introduced into the market, you will see resistance appear in people with that particular bacterial infection. Antibiotic resistance exist naturally in the soil as well, right? You want resistance so that you can survive the onslaught of, these chemicals that are coming at you from your competing microbes, right? And so there's kind of this competition happens in nature, and we see that played out in the human body as well. So increasing resistance, but also antibiotic discovery has plummeted because it's very expensive and takes a long time to develop new antibiotics. And so the pharmaceutical industry has largely abandoned antibiotic research. And so it's to academics to kind of step into this area of research. And so that's kind of how I am trying to address this challenge. The World Health Organization proffers that antibiotic resistance is potentially the most important medical challenge facing humans in the 21st century. And if no action was taken between now and 2050, the true cost of antimicrobial resistance would be 100 trillion and 300 million premature deaths. And so just the gravity of the potential that we're about to face. We thought that antibiotics, when they were first brought onto the market in the 1940s, that this was kind of the magic bullet. Dozens of antibiotics were discovered, but now we're seeing people are dying of previously treatable illnesses. And it's pretty scary to go to the hospital and not to be able to be treated or to actually acquire a resistant infection when you go in for some type of elective surgery or even non-elective. Go to the hospital to get well, you think, not to get a dangerous infection. All right, so turning to the Centers for Disease Control, they've come out with a report. This is their most recent report in 2019, talking about the antibiotic resistance threats in the United States, listing some of the top pathogens, some being an urgent threat, a serious threat, a threat of concern. And so it's a really readable report if you're interested in learning more. They propose some actions that can be taken to address this threat. First of all, preventing infection, controlling outbreaks, being careful in the hospital, tracking to know where outbreaks are happening, so collecting data. Antibiotic use and access, you can think of antibiotic stewardship. So how can we steward the antibiotics that we have to make sure that they're not also going to become ineffective? Vaccines, therapeutics, diagnostics, improving and doing research in those areas. And then also work in the environment and sanitation, again, to prevent infection. And it's in this area of therapeutics that I'm going to be talking a little bit. So therapeutics would be developing new antibiotics or new treatments even. It doesn't even have to be an antibiotic. There's other ways that are being proposed to deal with this threat. Some are very fascinating, okay? But I'm not going to give them any airtime today. So I've partnered with an organization called Tiny Earth, the Tiny Earth Network. This is headquartered at the University of Wisconsin in Madison. It was founded by Jo Handelsman, who is a microbiologist, soil scientist, has written a book on scientific teaching. So she's a very prominent researcher and also a very great educator, and has combined these two things into this program that helps instructors like me, teaching at a undergraduate institution, to draw students into this problem by doing a course-based undergraduate research experience. And so this organization has trained probably 700 some instructors just this past week. They were training 27 instructors in Madison. Those instructors then go and teach their undergrads. So there's thousands of students doing this project every semester around the world, in fact. And it's a pretty easy and low cost cure research experience to do in a microbiology lab. It can be scaled up to do at large universities. I work at a mid-sized university right now, about 6,000 undergrads. I taught 4 sections of my microbiology course this past spring and was able to do this project impacting about 60 students with a semester-long authentic research experience. And so the methods, basically, students bring in Yeah, let me go to this one. They bring in soil, and I'm from Minnesota, and I teach in the spring semester, which is a total misnomer because it's not spring in February. And so my students are very disappointed when they have to go find soil in Minnesota in February. But they do it. Most of the time it's next to a dryer vent outside the dorm where the snow has melted. But there's plenty of bacteria in there. So they bring in the soil, and then they plate that soil on various types of Petri plates and culture a diversity of microorganisms. And then they create kind of a plate here with 24 isolates. We call this the library plate. And I'll just mention something right now. When I first started doing this, we called it the master plate. And that term is going out of use, master, because it's referring to colonialism. Okay? And so I'm retraining myself to say library plate. Even a master key or a master bedroom, you might want to consider your language. Anyhow, moving on. Students then screen these 24 colonies on their library plate by patching them to another Petri plate that's been spread with a tester organism that mimics a bacterium that's of concern as far as being untreatable by antibiotics. So it's kind of a stand-in for a pathogen. Has features that are similar to the pathogen. So we're hoping that we can find a bacteria that competes well against this pathogen. Okay? And you can tell if it's producing an antibiotic by what you see here, we call a zone of inhibition. So around that bacterial isolate, there's no growth of the tester strain that's been spread over the plate. Okay? And so on this plate alone, there's four or five candidates for bacterial isolates that produce an antibiotic. So the hope is that one of these might be a novel structure, a novel antibiotic. Okay, but we don't know that at this point. We don't even know what the isolate is from the soil. And so in class, students are identifying the bacterium by doing some 16S rRNA gene PCR amplification. They're having it sequenced. They're then doing some bioinformatics to figure out what genus. And even if it's a genus that we have seen before, which most of the time it's going to be, that doesn't mean that there's not a novel antibiotic being produced. So there's a lot more work that actually needs to be done. And we can't do all of that in a semester. And so the beauty of Tiny Earth is that isolates from my students can then be sent to what we call the Tiny Earth Chemistry Hub, which is an arm of Jo Handelsman's lab. And she has a team of researchers, small but mighty, that do further work on the isolates that all these undergraduates around the world, actually around the US, are sending. They haven't figured out how to have microbes sent from other countries to them yet. They do metabolomic profiling and genomic sequencing. So actually they start out with the genomic sequencing. And so they isolate the genomic DNA, they send it out to a sequencing facility who sequences the entire genome, and then they do some bioinformatics to see if there might be some novel biosynthetic gene clusters. These gene clusters are a series of enzymes that could produce a secondary metabolite, such as an antibiotic. Okay? So you can make predictions based on the genetic sequence. Oh my gosh, here's a biosynthetic gene cluster that's not similar to anything we've seen before. We want to maybe study that isolate and see if there's a novel chemical structure that could be a novel antibiotic. So they start at the genomic side. If they get some interesting candidates, then they do some metabolomic profiling. So they do some chemistry, they do extractions, they do some mass spec, they try to figure out the chemical profile, and then maybe the structure eventually. And it's hopeful that there's going to be this funnel, and eventually we'll purify and develop a new antibiotic, kind of using undergrads to be at the top of the funnel. So this is the work of the Chemistry Hub that I've just outlined. This is how many they've done to date as far as genomes that have been sequenced, metabolomes analyzed. They have 22 high priority isolates. These are isolates that have good potential. And I just love the fact that I can show this slide to my students and say, my students have have submitted samples that are some of these high priority isolates. So we have at least 12 genomes that Tech has sequenced from my students. And some of those are high priority isolates. And so this is connecting my students to a real research project that's maybe making a difference. And how transforming is that for an undergraduate to be invested in such a way, to be involved in a larger scientific community. And that's what I just love about this network, because there is a network of other scientists and educators that can support me. I'm not just doing it myself. So we'll move on to the transformative education piece. I'll talk a little bit about the science of soil maybe at the end if I have time. But that's a kind of an introduction to antibiotic resistance, the problem, the crisis, and how we're going about solving it. Now, this transformative education piece, I've given you some teasers. I think you can kind of recognize that this can be transformative for a number of students, a large number of students, right? And so when I was an undergraduate, I sought out a professor. I said, hey, I want to do undergraduate research with you. It was kind of a one-on-one mentorship, or me in a small lab with a graduate student or postdoc. Not every student's going to have that opportunity. It's not really cost effective for at a small school for us to educate all of our students in that way. Maybe we can't. And so to do it in the context of a course is really, helpful for all the students to have a research experience, because research is really the dance. It's why we became scientists, right? It's not to read textbooks. It's not to memorize facts, but to be a scientist is to do some research. And so even if they're not ever going to do research as a career, I think it's valuable for them to have that experience. And not just, so I've taught this to, biology majors, pre-nursing students. I've taught it to non-majors. So if you're talking about science communication, for a non-science person, they label themselves as a non-science person, to know how research is done, to know that, hey, we make mistakes. Hey, this is hard. Hey, the scientists really know what they're doing. Hey, I can be a part of this. Hey, I can understand this. It's a great way to build scientific literacy, is to actually be involved in a science research project. And this is a very accessible project that most students can relate to and understand. All right, so course-based research experience, there's lots of educational research talking about this as being a high-impact learning activity, like doing an internship or doing some service learning, doing research, obviously high impact. It can increase student persistence in science, so I have references to that effect. It builds students' identities as scientists. They can now vision themselves as being a scientist. And it can contribute to equity in science by providing opportunities to all students, including those historically underrepresented in the sciences, who might not know how to get into a research lab or not have, the knowledge or confidence to do that. But now they're brought into this community of scientists, given an opportunity along with everybody else. This shows some of my students in action here at St. Thomas. And so, research says the benefits of cures. What do the students say about this? So here we have Maggie, and she wrote, I loved working with the Tiny Earth Project since it was real research, what felt like I was contributing to research being done by scientists, and I had the chance to advance science for the common good. And I love Maggie because that's like our mission statement, all for the common good, right? So she's drunk the Kool-Aid at St. Thomas, right? So she put that into her comment. All right, another student wrote, the lab prepared me well for research in biology as a whole, but specifically microbiology. I'm confident in pursuing research opportunities in the microbiology department. The reason I haven't pursued research opportunities is that I haven't been confident in my abilities to provide meaningful input into a team, or that I wouldn't know what to do. Okay? And so this course instilled in me the knowledge and understanding to perform all tests in lab and how to operate all equipment to the point I feel confident enough to do it in a job in some microbiology lab. So they're even feeling confident enough to be employed after graduation. I really liked the way this lab was run and how we focused on one big research project throughout the semester. I enjoyed the hand-on aspects It's been the most engaging lab I've been a part of being at St. Thomas. So even if there's no evidence that they're persisting more, they're feeling good about their education. I'm feeling good. We're enjoying the lab. This shows some students doing the research, but then also presenting. And so science communication, you gave a talk on that yesterday. And so here's students preparing posters on their research. That's a main method of communicating science. And so this is on our campus, and this is actually a Tiny Earth symposium, so an annual symposium in the summer, students coming from all over the country to present their research to other undergrads. And so they're seeing, like, what is a real scientific conference like? And I can present at this, and I can do this hard thing. So again, transformative education. All right, I'm going to put this up. This is a logo of Tiny Earth. You've heard a little bit about Tiny Earth. If later on, you can look at that website, Student Sourcing Antibiotic Discovery. Just look at this logo right here. And I don't want to lose you all, but what do you see? What images? Like, why did they choose this logo? Think for 10 seconds. Can we be brave? Like, we're not students. Like, we can shout out, what do you see?
It looks like it might be something you'd see through a microscope.
Okay, so maybe you see microbes. Okay.
People at herbs.
Oh my gosh, you have great eyes, because I didn't see that the first time. So there's the heads, right, of the people, and they have arms. And what are they doing, those arms? They're connecting, they're embracing. What color are those people? All colors.
Sorted colors.
Yeah, a range of colors. They're also the color soil. Mm-hmm. Other things you guys might see.
Brown for earth.
Round for earth.
And round. Brown and round.
Brown and round, yeah. Maybe you see colonies on a Petri plate versus just under a microscope. So all kinds of stuff going on there. And so here's my segue to fostering the love of God and neighbor. One of my kind of life verses here, this is why I do science, right? Hear, O Israel, the Lord our God, the Lord is one. Love the Lord with all your heart, with all your soul, with all your mind. That's what I do. That's how I love God. And with all your strength. The second is this, love your neighbor as yourself. There is no commandment greater than these. Another really important verse to me and to many people. He has shown you, O mortal, what is good, and what does the Lord require of you? To act justly, and to love mercy, and to walk humbly with your God. And then finally, we heard this morning at the keynote. I saw, this is from the message, I saw a huge crowd, too huge to count. Everyone was there, all nations and tribes, all races and language. This is just beautiful to me. What the kingdom of God will look like, what it should look like here in my mind. And so whatever I can do to create that, welcome here. And so the Tiny Earth Network has really worked hard in this area of AJEDI, anti-racism, justice, equity, diversity, inclusion. They've published a paper here, AJEDI in Science, leveraging instructor communities to create anti-racist curricula. So I'm part of an instructor community, and I'm getting ideas from my fellow TEPIs, they're called, Tiny Earth Partner Instructors. By the way, students that take my course are called Tiny Earthlings. Isn't that cute? I'm not sure that they like that, but in this paper, they have a definition of, these 5 terms, and something I've incorporated into my course to kind of just, how do you naturally talk about this in science courses? There's ways to do it. One way is just say, hey, there's this paper, Tiny Earth Instructors, we're really invested in this. Here's this paper. I assigned each of the students one of those 5 kind of principles. And then I asked them to discuss. We did the steering lab for an hour. This was important to us, to me. I said, how have you seen shortcomings in STEM in regard to each of the AJEDI principles? So if they were talking about, justice, how have I seen a lack of justice in STEM? Or how have I seen STEM move towards justice? What are examples of diversity, seen or unseen, that are present in members of our classroom community? I think it's really important, especially to think about the unseen diversity, okay? A lot of focus on, differences in how people appear or present, but, all kinds of mental health and, hidden diversity It's important to be mindful of that. How can we be mindful and respectful in our formal and informal interactions? So I need to make a safe classroom environment, but they also need to make a safe classroom environment for their peers. And even when they're doing lab experiments, it's just, they're just having conversations. How is what they're saying maybe impacting other people at their table, right? Maybe they're talking about partying on the weekend and somebody's in recovery. How's that impacting them? Be aware of that. And so just trying to get this out there in the open. And then lastly, a land acknowledgement. So we're dealing with soil. So to acknowledge the soil on which we stand is something that I've done. Okay. I've been very intentional about including a syllabus statement as a result of my Tiny Earth training. So just be very explicit that we welcome the diversity that's benefiting us, and we won't tolerate racist behavior or hurtful language. Okay, and I'll talk about, I'll give the land acknowledgement. The land acknowledgement is in my syllabus. And then we'll revisit it. Like, why do I put this in there? Why did I talk about this? And then this is a wonderful paper. I probably won't have time to talk a whole lot about this, but she's Beronda Montgomery is a microbiologist. Lessons from microbes. What can we learn about equity from unculturable bacteria? So rather than looking at a deficit model of students, what are they lacking? Why aren't they doing well in our classes? Well, what are our classes like? How are they not supportive? It's not a good culture for them to thrive. How can I change the culture? So this is a good vignette to introduce AJEDI topics into your course. All right, I didn't have time to talk about soil, but Joe Handelsman has given lectures and has written a book called A World Without Soil. And so to think about that is another way to draw microbiology into a larger discussion. All right, acknowledgements. Thank my department, my students, the Tiny Earth Network, ASA, and there's kind of a news story. If you want to hear more about Tiny Earth, about my research, you can read more at the St. Thomas Newsroom story. So thank you, and some references, and
Thank you, Joanna.
I have just one question is, how do you control, because this is related to the bacteria culture, right? How can you control maybe this bacteria is dangerous?
Yeah. So we do run a BSL level 2 lab. Yep. And so students are wearing goggles, protective material, gloves, and we don't grow liquid cultures because those are more dangerous. And then if I think it's a bacillus, I'm probably going to autoclave it because you might have bacillus anthracis or something. But we haven't had any dangerous ones. But doing the sequencing before we do much other work is one way to do that.
Thank you so much.